and it contradicts the energy conservation. So this fact underlines the basic situation about the Euler equations, that it's very important to define what do you mean by a solution. And there are various notions of solutions of the Euler equations. So on the left-hand side are the classical solutions, that's when V is in the Hölder space C1 alpha, or in a sufficiently high Sobolev space. And as I mentioned, this is the local Verposeness result, and the energy is conserved. On the very other end of the spectrum, there are several very weak notions. They are very weak in the sense that it's either not a function V, but only a measure, or it's a function, but it does not satisfy the equation. It's the dissipative notion of solution due to Pierre-Louis-Lyon's. On the other hand, because for these very weak notions the space is enlarged sufficiently, it's not difficult by soft arguments to prove existence. But one would not expect even uniqueness in this class. And in the middle there are several weak or distributional notions, and I made the distinction between weak and distributional also because you can define a weak solution by something more classical than distributions, by just looking at volume elements. But both of these classes, weak solutions or distributional solutions, exhibit a very wide behavior, or H principle, and this is the subject of my talk. So I want to spend a few minutes describing what is, at least to my mind, to a PD person, the H principle of Gromov. And so I'm quoting from a wonderful paper of Gromov from 1999, and so it's best to explain the H principle by first telling you what it is not. So this is the local to global principle, as Gromov explains it. So I'm quoting, the main paradigm of classical physics is the non-existence of non-local interactions. Not surprisingly, we expect observable physical patterns, e.g. positions of moving particles after a given time interval, to be predictable in terms of local laws, and the presence of a particular microscopic law should be manifested by a specific global behavior. So, roughly speaking, the microscopic or local laws are partial differential equations, or differential equations, and by integrating these differential equations, one should be able to deduce the evolution or global behavior of the system. And in geometry, the examples are the notion of length. You define length by metric, which is an infinitesimal distance of particles, or think of a chain of beads, and by summing up the infinitesimal distance, or integrating, one gets length. That's a local to global notion. A more complicated local to global notion is the rigidity of closed surfaces, or isometric embeddings. The classical theorem is that the standard 2 sphere is rigid in the sense that there are no non-trivial isometric deformations. So if you try to bend the standard 2 sphere, it's just not possible, it's rigid. Of course, Gromov was well aware of this example. This is an example of an embedding of a flat 2 torus into 3 dimensions, which should not be possible in the smooth world, but it is possible using the Nash-Gromov embedding. And this is a picture by Vincent Borelli and his team, and I will come back to the details of this picture. So the Nash-Gromov theorem, that is the basis of the previous picture, is an example of the H principle. Quoting again from Gromov, the H principle is when the infinitesimal structure of a medium does not affect the global geometry, but only the topological behavior of the medium. So I've quoted the Nash-Gromov theorem. It's the following: any short embedding of a compact Riemannian manifold can be uniformly approximated by a C1 isometric embedding. So how is this useful to explain what Gromov means? So here is my picture of the flat 2 torus, and the medium that we are talking about here is the surface. It's the 2 torus, or its realization in R3. And there is a topological aspect of embedding. If you can even find a topological embedding of a 2 surface into R3, it's a non-trivial question. In the case of the 2 torus, you can just embed it as the standard 2 torus, which is not flat, into R3. And then you can just, using a homotopy, shrink it, and that becomes then a short embedding. Short embedding is just an embedding that shrinks distances. So it's easy to find a smooth short embedding of the flat 2 torus. And then the Nash-Gromov theorem says that in the neighborhood of this small 2 torus, there exists C1 isometric copies of the standard, of the flat 2 torus. And they will be very much curled up. And that's the, okay, so that's the third picture. So basically the idea is that there is a topological condition and a differential condition, but the H principle is a principle that means that in such situations the differential condition is not important. Once the topological condition is satisfied, you can locally wriggle the solution in order to also satisfy the differential condition. Gromov continues to say that the class of infinitesimal laws subjugated by the homotopy principle is wide, but it does not include most partial differential equations of physics, with a few exceptions leading to unexpected solutions. Now, why it does not include the partial differential equations of physics is precisely what I explained with the local to global principle, that for a PDE in classical physics, one would expect a unique solution. And so more generally Hadamard's notion of well-posedness. Whereas if you look at a typical PDE from geometry, it might be highly underdetermined, or it might have a huge invariance group, so one does not expect uniqueness. There might be a huge flexibility in finding solutions, or designing solutions. So when Gromov talks about unexpected solutions, he's citing this paper of Müller and Schwerak from the proceedings of the ICM in '98 in Berlin. So I want to say a few words about what is contained in that paper. So the paper is about solving differential inclusions, but applying it in very unorthodox and surprising ways. And to start with, I want to give you an example of a physical situation where one does not expect uniqueness. That's nonlinear elasticity. So the basic setting is that there is an elastic body which is referenced by a three-dimensional domain omega and a deformation u. And the model is that this deformation is supposed to minimize a certain elastic energy, which is integral of some function w of the gradient of the deformation. And so, for instance, you take your elastic body and deformation means you're applying a boundary condition, and the body is supposed to accommodate inside itself towards to minimize the energy according to this boundary condition. That would be one example. And so in this elastic problem, one does expect non-uniqueness. There is the classical Euler-Buckling situation, and there are microstructures in certain metal alloys where uniqueness is not the correct question. So I'm not explaining to you what are microstructures, but just giving a couple of pictures. Think of these as pictures of atomic lattices where the different colors mean a different local arrangement of the lattice. And so it's already pretty clear from the picture that uniqueness is the wrong question. The correct question might be more of a statistical nature, such as what are the volume fractions of the different colored regions? Or another question, more in the light of Gromov's philosophy, is how does a specific type of microstructure influence the macroscopic global behavior of the material? This local to global question. So a first step towards studying this problem is by replacing the integral, the variational problem, by a differential inclusion. So assuming, without loss of generality, that this function w is non-negative, we just study solutions u whose gradient lies in the zero set. So this is a differential inclusion given a set K, characterize solutions u such that du is in K. And there are two types of objects that one can study, either approximate solutions, which leads into the theory of gradient Young measures, or exact solutions, which is what I want to talk about now. So, in this elastic problem, there are two types of situations. The simplest one is when the set K is just the set of rotations. That would be the case that microscopically the atomic lattice does not allow for any zero energy deformations. But of course it might, so except for rotations, there's a rotational invariance in the problem, obviously. And so it means that we are looking for maps whose derivative is a rotation at every point, or almost every point. The other type of situation is where there are certain preferred directions at the microscopic level, and this leads to several copies of SO3. So 2 in 2 dimensions, 3 in 3 dimensions, or even more in different lattices. And the typical theorems are the following. So in the first problem, if the mapping has a gradient which is almost everywhere a rotation, then it has to be globally a rotation. Of course, a priori, it could be a different rotation from each point, but that's what the theorem says. So this is an example of the local to global principle, or rigidity. The other situation is completely different. So locally, it's not true that I'm allowed any affine deformation of the lattice, but globally I am. So the statement is that for any affine transformation that is sufficiently close to the identity, there exist solutions of this differential inclusion which equal to that affine map on the boundary. So this is somehow liquid-like behavior. Okay, so I want to now spend some time discussing how to solve differential inclusions. And there are basically two approaches, and both can be easiest explained by forgetting differential and just looking at inclusions. In particular, just considering the following toy problem: construct functions with modulus 1. So it's the inclusion, K is the set consisting of 2 points, plus and minus 1. The first approach is using bare category arguments, and the basic statement is the following: that the set of functions with modulus 1 is residual. So in the bare category sense, it's a huge set in the set of functions with modulus less than or equal to 1, with respect to the L-infinity weak star convergence, weak star topology. So the set of functions with modulus less than or equal to 1 can be metrized. It's a bounded set in L-infinity, so this is a metric space, and in this set, the set of functions with modulus 1 are residual. So most functions, modulus less than or equal to 1, actually have modulus equal to 1. It might be a surprising statement, but it's a statement that is related to a classical statement in functional analysis that in the weak topology, the extreme points of a set are dense. Okay. So that's the kind of functional analytic core of how one studies differential inclusions. And the same kind of argument leads to statements for real differential inclusions. For instance, that any one Lipschitz map, which would be a short map, but now in the Lipschitz world, it's just a one Lipschitz map, can be uniformly approximated by Lipschitz isometries. So solutions of this differential inclusion where now the gradient is supposed to be an affine isometry, almost everywhere. So another way of saying it is that affine isometries are dense in one Lipschitz maps. And the same technique applies also to the Euler equations. So here the statement, which is a slight improvement of Scheffer, is that there exist infinitely many weak solutions which are bounded of the incompressible Euler equations with compact support in time. So here you should think of solutions of the Euler equations as the extreme points of a certain set. And so we are speaking of a nonlinear equation. It's a nonlinear set. We have to take in a clever way the weak closure. And in the weak closure we obtain functions which are much easier to construct. And then we can use this bare category machine to show that, in fact, once you can construct a lot of these functions, weak solutions have to be in the neighborhood of any of these functions. A slightly more surprising statement is that you can even prescribe the square of the velocity. So given any function, any positive function e of x and t, there exists infinitely many such distributional solutions where 1/2 v squared is equal to e. So now we have completely left the realm of evolution equations. This has nothing to do with evolution because I can just tell you what is the modulus of v for any time in any space. And so telling you what is the modulus, the only thing that can change is the direction. And there are analogous statements to many other types of equations, such as the compressible isentropic Euler equations and the large class of active scalar equations, such as incompressible porous media. Okay, and the third statement I want to mention in this group is the following: that any measure-valued solution of the Euler equations can be generated by a sequence of distributional solutions. So I don't want to define what is a measure-valued solution. It's a notion where you replace a function, the velocity, by a measure-valued object, measure-valued function. So instead of having a fixed velocity, now the fluid there's a measure for every xt in the space of velocities. And so there is a huge scope of non-uniqueness for measure-valued solutions. And then this theorem says that it's the same scope of non-uniqueness for distributional solutions. In other words, the set of distributional solutions in some sense coincides with the set of extreme points of the set of measure-valued solutions. Okay, so that's the bare category method. Now I want to also discuss the second method, which is more constructive. So going back to the toy problem, let me just consider this very explicit scheme. Of course, you can cook up many schemes that look similar. So it's an iterative scheme of how to construct functions of modulus 1. And given Vn, I define Vn plus 1 to be Vn plus a fast oscillating function with a certain amplitude that depends on how far Vn is away from being modulus 1. So Vn is supposed to be a sequence that converges to modulus 1, and so the amplitude of this perturbation will be proportional to the error somehow in my differential inclusion, and then it's multiplied by some, you can take sine function or this sine of sine, so plus and minus 1 and periodic with some frequency, which is imagined to be very high. And the amplitude is also hooked up in such a way that if Vn has modulus less than 1, then Vn plus 1 also has modulus less than 1. And it's not very difficult to show that this, if lambda n converges to infinity sufficiently fast, this sequence will converge to strongly to a function of modulus 1. And so here are some of the pictures. As you see, it will start to oscillate very widely between somewhere close to plus 1 and somewhere close to minus 1 after already a few steps. So it's not very exciting, but what is interesting is to understand the rate of convergence. Of course, then you have to declare what is lambda n, and one can prove the following simple lemma, that if lambda n is 2 to the n, so I'm really taking a dyadic sequence, then the rate of convergence is exponential. Now, what is interesting about this is that this rate of convergence, this integral of 1 minus Vn squared, is the integral of the amplitude. So I'm saying that there's a frequency which is growing exponentially, but the amplitude is decreasing exponentially. So in some sense, it means that this limit function is not going to be the worst possible function of modulus 1. It's not a typical L infinity function. It will be a function with some slightly better regularity in some fractional Sobolev or Besov space. And so this question whether the technique of this iterative scheme can be pushed slightly beyond the natural regularity, this question has been studied also for the Nash-Kuiper theorem. So in the Nash-Kuiper theorem, I will come back to the proof in a short while, but it's a similar kind of scheme where at each step you add a high frequency oscillation, and the natural space where things will converge is in C1, but you can prove that the Nash-Kuiper theorem will remain valid for functions that are slightly better than C1. They are C1 theta, so in a Hölder space with exponent theta. And this theta will depend on the dimension. Okay, and it will be a very small theta, because if the Hölder continuity would be of too high exponent, then one would also reach the rigidity regime of the classical theory. And the same type of game can also be played for the Euler equations. Here's the statement we have. For any smooth positive function of time and any exponent less than 1/5, there exists a weak solution with this Hölder continuity, and such that the energy is equal to E of t. So the energy is independent of the evolution. You can prescribe whatever you want. And this was now joint work, which was just very recently accepted in the Annals of Mathematics, joint work with Bookmaster, Del Ellis, and Phil Issett. Many of the ideas in this paper came from Issett's PhD thesis, and there was a previous paper by Camillo and myself where we had a similar statement, but with 1/10 instead of 1/5 being the Hölder continuity exponent. And there's also a uniqueness statement. So you see here in this theorem, I'm not talking about uniqueness, I'm talking about whether the energy is conserved or not. Okay, so there is still ongoing effort in increasing this Hölder exponent. So I want to explain why one is interested in this Hölder exponent. And this is the second part of the title of my talk, Turbulence. And so to begin the story, one considers the Navier-Stokes equations, and I've written 1/Reynolds number to just signify that there is a certain scaling involved in a lot of things that I'm going to say now, but think of it as Reynolds number being large, 1/Reynolds number is small. So if you take the Navier-Stokes equations, by the same formal calculation that leads to energy conservation in Euler will lead to energy dissipation at a rate which is proportional to 1/Reynolds number. So in particular, if the Reynolds number goes to infinity, formally the energy dissipation rate should go to 0. But what is known from experiments and simulations is that it does not. This is known as dissipation anomaly in three-dimensional turbulence, and it's a very much studied phenomenon. Now, the mathematical foundation of turbulence was laid down by Kolmogorov in his statistical theory, what is known as the K41 theory, based on, so he did not consider single solutions of the equations, but ensemble averages of solutions of the Navier-Stokes equations with respect to some unspecified measure. And then he stated some hypotheses. Let me just concentrate on the third hypothesis. This is the hypothesis that there is a finite non-vanishing rate of dissipation. So there is a positive epsilon such that the rate of dissipation is at least epsilon. This is a hypothesis based on experiment, and so then based on this hypothesis, he derived various scaling laws for certain quantities of this ensemble average, one of which is a decay on the energy spectrum. The energy spectrum is basically the decomposition of the total energy in the different wave numbers. Wave number lambda, E of lambda is the energy density at wave number lambda. And Kolmogorov derived the following law, that the energy at wave number lambda is proportional to lambda to the -5/3, at least in a certain regime of wave numbers where the viscosity has a negligible effect. And this -5/3 agrees very well with the experiment. So here is a log-log plot of an experiment where you see that the slope is -5/3. So more or less at the same time, Onsager, who later got the Nobel Prize in chemistry, but he made very important contributions in statistical mechanics before, also studied this problem of anomalous dissipation, but from a different angle. So he was really looking at single solutions of the Navier-Stokes equations. And in particular, he said, one may inquire about the laws of dissipation in an ideal fluid. So let us take the Reynolds number formally to infinity. So formally we obtain the Euler equations, and let us ask, is it possible that solutions of the Euler equations dissipate energy? And then I went on to show that, in fact, it's possible to show that the velocity field in such ideal turbulence cannot obey any Lipschitz condition of the form written here, with theta greater than 1/3. So in modern terminology, he's saying the following: consider a weak solution of the Euler equations with this Hölder continuity with exponent theta. If the theta is bigger than 1/3, the energy is conserved. And if the theta is less than 1/3, dissipation is possible. So in this sense, 1/3 is the sharp exponent. Now the first part of the conjecture was essentially proved by himself and later rigorously by Eying, Konstantin Titi, and refined into scales of Bezov spaces as well. And in my talk, I want to concentrate on the second part of the conjecture, how to construct solutions with theta less than 1/3. And so you see we have reached 1/5, and we are trying to reach 1/3. Maybe let me also mention that this 1/3 exponent of Onsager exactly corresponds to the -5/3 decay of Kolmogorov. Okay, so if you interpret that as a decay on the Fourier coefficients. Okay, so in this slide, I want to give a short sketch of the proof that is due to Konstantin E and Titi of the energy conservation if we assume that this exponent is bigger than 1/3, because there is a slight subtlety. So the argument is to take a solution V, P, and mollify. So we have V epsilon, P epsilon, and since the mollification, we have a nonlinear equation, so there will be an additional term that I put on the right-hand side, which consists of a commutator between mollification and taking the product. Now, since everything is smooth, you can write the energy balance. So the energy at time capital T minus the energy at time 0 will be given by this term, an integral in space and time of gradient V epsilon times this commutator. And the goal is to show that as epsilon converges to 0, this right-hand side converges to 0. And now assuming that V is a Hölder continuous function, the gradient of V epsilon is going to converge to infinity, but at a specific rate that is given by the Hölder continuity. So it will converge to infinity as epsilon to the theta minus 1. On the other hand, the commutator will converge to 0. also at a specific rate, and the estimate that is slightly more tricky than the estimate on the gradient of V is that I wrote down, you have a rate of epsilon to the 2 theta. So in total, the right-hand side will be bounded by epsilon to the 3 theta minus 1. So if theta is bigger than 1/3, the right-hand side converges to 0. More precisely, if the L3 norm in time of this Hölder norm in space of V is bounded, then we have the convergence. So if you're more careful with the estimates, you will get this kind of statement. So, in Onsager, there was no mention of time. And it's really a problem about the regularity in space. But there is this slight subtlety that the third power of this Hölder norm needs to be integrable in time. Now, in the effort of pushing the exponent towards 1/3 from below, Bookmaster managed to show that it's possible to do this for almost every time. So there are solutions which do not conserve the energy. So here we are not specifying the energy, but we're just saying the function has compact support in time, which means it cannot conserve the energy, such that for almost every time the function is a Hölder continuous function in space with this exponent. But of course we don't know how the constant depends on time, and this year we managed to improve that to integrability in time. So now you see that comparing with the previous result of Constantin Ititi, what is missing is the exponent, is to improve the exponent 1 to 3, to close the gap between energy conservation and energy dissipation. So let me spend a few minutes explaining how Nash proved his theorem in order to give you an idea of how these constructions work. It's slightly more complicated than the one-dimensional case. It's a lot more complicated than the one-dimensional case. So here is again the Nash-Kuiper theorem. I've restated it. And so being an isometric embedding in local coordinates means satisfying this set of partial differential equations. So G is a given metric, and we want to find U, such that this holds. Whereas being a short embedding means that this difference is positive definite. Okay, so the idea of Nash, so Nash considered the case of codimension 2, and the basic idea is that if you want to increase the metric without going too far away from the surface, or the manifold, it's easiest to make a kind of spiral, or a little wriggle, that will increase the length without going far away. And here is the specific formula of Nash for increasing the length in a fixed direction. So again, there's a frequency lambda, which is supposed to be large, an amplitude that will depend on x, and there's this high frequency spiral parameterized by sine and cos in a certain direction, psi, in the domain. And so when you make the computation of what is going to be the new metric, you get that the new metric is the old metric plus a term of this form, which just signifies that the metric increased in the direction of psi by a squared, amount of the amplitude, plus there is a little error, an error that is small if lambda is big. So this kind of spiraling perturbation has the effect of increasing the metric in a very controlled way in a single direction by exactly the amount that you want, by a squared, which you can just put whatever you want. And so the idea is simple. We take our short map, and G minus the induced metric is positive definite, so we decompose it into a sum of such primitive terms, and it's a finite sum, number depending on the dimension, and then add these spirals one by one. So there's U1, U2, U3, and so on. Each one is a spiral added on top of the previous embedding, with the effect that the metric will have been increased by exactly this amount, this primitive term, plus an error. And in order to control the accumulation of these terms, the frequencies have to increase very quickly. And after this finite iteration, we obtain a term that is almost the correct metric up to the error. So we will need to iterate this to successively remove the error. But the crucial estimate is that the C1 norm of the difference is controlled by the amplitudes of the spirals. And the amplitudes in turn were defined by decomposing the previous metric error, so they are controlled by the previous metric error to the square root. And in particular, if it means that if in the next iteration, if the metric error decreases to 0 sufficiently fast, then the scheme will converge in C1. So at the end of the day, after an infinite iteration to remove the error, we will obtain a function of this type, where there is a kind of inner iteration, where each of these terms is one of these spirals, and they have to be adjusted, of course, according to as the iteration goes on. And here's the picture. So starting with the standard short torus, the first iteration is in this direction. You see it's just simply a corrugation. And then on top of that corrugation, there is the second corrugation, and the third corrugation is difficult to perceive, and so on. So it will be a more or less similar figure with these spirals added on top of each other. Corrugations in this case, because it's who dimension 1, not 2. So this is what we want to do for Euler. And so instead of a metric error, we are going to have an error. So this VQ we think of as the approximation of the solution. And there is an error which we write in this form, as a kind of Reynolds stress. The reason being that this is what one would get if one if one starts the opposite way. If one starts with the oscillating solution and averages out the oscillations. Okay, so basically the next term, VQ plus 1, will have this ansatz. It's VQ plus a fast oscillating velocity field, which depends also on the slow variables. And so this is our analog of the Nash wrinkle. And this is supposed to satisfy a certain set of properties. First, it has to be periodic in the fast space variable. So this xi tau is the fast space and time, xt is the slow space and time. In the fast variable, it has to be periodic with average 0. This denotes the average in integral in xi. And the average stress is supposed to be the previous error. RQ was the previous error. So the idea of Nash, if you interpret it correctly, is that in the oscillations, the dominating term is not the linear term, because it's fast oscillating, so in a weak norm it's almost 0, but the quadratic term. And the quadratic term is the one that is supposed to cancel the previous error. So this is what the scheme is supposed to do here as well. And then in the fast variables, we have to satisfy the Euler equations. I mean, if you plug in that ansatz to the equations, you will get a lot of terms with fast derivatives, and they should be 0. Okay, so what is new compared to Nash is that we don't have additional dimensions. So we cannot really make this linear part of this equation 0. That's made 0 by always making, in Nash, by always making the perturbation orthogonal to the previous manifold. And this, okay, the interpretation for us is that this is the convection of the microstructure. So VQ is the previous solution, so it's macro flow, and the W is the fast oscillation. On the other hand, we are in good shape concerning the other part of this equation, because there is, in fact, a family of stationary solutions that we can use. And these are the Beltrami flows. So Beltrami flows are a special set of solutions of the stationary incompressible Euler equations, which arise from the eigenspace of the curve operator. And so they all have this form, bk times an exponential, where modulus of k has to be lambda, and the bk is cooked up according to some algebraic condition. And if lambda is big, this is a pretty high-dimensional space. And so we can take a combination of such Beltrami flows with coefficients that depend on the slow variables that appear implicitly in the old Reynolds stress R and the old velocity V. And so the old Reynolds stress R appears to define the amplitude just like in Euler, because so this is cooked up in such a way so that the average of the W tensor W is R, and this phase we would like it to be this function, this exponential, in order to kill the linear term. This doesn't work exactly. This was our first try. A slightly better ansatz is to modify the previous ansatz a little bit and use the inverse flow. On the other hand, this is the inverse flow of the previous approximation. It is converging to a Hölder continuous function, so there are very bad estimates. So it's only controlled for a short time, and so it has to be cut off in time and then restarted. And that leads to additional errors, and then somehow the basic stumbling block where we are stuck with 1/5. We could improve it to this L1 of 1/3, but not really the full result. So the basic problem is how to transport the microstructure by a macroflow. So to conclude, let me go back to this paper of Gromov. So he says that, in fact, the presence of the H principle would invalidate the very idea of a physical law, as it yields very limited global information by the infinitesimal data. That's exactly what I said earlier, that for a physical PDE, one would not expect the H principle. But I would add that it seems the H principle applies in certain physical situations where one is more interested in a statistical description, such as in the elasticity problem. It's more the characterization of the underlying Young measure or volume fractions, not really the uniqueness. And in turbulence, it's also the K41 theory that is best suited to explain certain phenomena. And in such situations, one is led to consider solutions with low regularity. So that's it. Thank you very much.
Are there any questions?
Well, you talked about energy dissipation, but dissipation means loss of energy, decrease in time of energy. Why? If you have something with complex support in space-time, this means that the energy is zero initially, it is zero finally, and since it is non-negative, it must be positive at some point, otherwise it's zero at all times. Okay, so this means that there is gain of energy, and not only loss. And gain of energy is contrary to the second law of thermodynamics, and it has never been observed that the second law is violated. In fact, Einstein remarked that it is the most well-established law in all of physics. What do you say about that?
Of course, if this would be observed, we would solve the energy crisis, if you could just create energy. More seriously, so I've just discussed the Euler equations and several types of theorems. In certain theorems, we can prescribe the energy. Of course, then you can make the energy monotonic decreasing, not contradicting the second law of thermodynamics. In these final theorems, because we are pushing the 1/3, we are forgetting the physics, and so there we can only produce compactly supported solutions. But it's a technical thing, just in order to convince the reader that the energy is not conserved.
But since there exists, since if I start with smooth data, there is a smooth solution for a short time.
Yes. No, I understand.
Original classical results show. The question is whether this solution breaks down, and from some point on, you can continue with some generalized motion, for which, however, the energy is decreasing rather than increasing.
That might
So this
be.
would be something which is physical.
But, okay, so you can consider an initial data and then produce solutions by these methods where the energy is strictly decreasing and non-unique. Of course, then the question would be, can you select one that is physically relevant? That might be through the viscosity approximation, but I think there are arguments supporting that even the viscosity limit would not be unique. But coming back to the theorems I stated, just the Euler equations, so unless you either make it an extra condition or put an extra equation, it's not possible to talk about the direction of time. It's invariant. On the other hand, when I speak of the initial value problem, for rough solutions, it seems to be a different world from when you speak about the initial value problem for smooth solutions. And I don't know if you can pass from one world to the other. In fact, I don't know physically what it means to speak of the initial value problem for Euler for rough initial data, because it's highly unstable.
Okay, thank you very much.